much for joining us here today, and thank you very much for your patience. Sean Kelly has been able to join us here, which is good because he is our presenter for today, so you're in the right place if you are here for our presentation on the boost converter and the FCC requirements. And so what I'm going to do at this point is I'm going to change the presenter over to him, and so let's make him the presenter here. So Sean, you now are going to have the comm.
Welcome to part 2 of our 2-part series on DC switchers, problems and solutions. So since we're running a little behind, I'll go ahead and get started. So the purpose of the webinar series we started last month is to help those of you who have very little background in DC-DC switcher design by giving you some practical understanding of how they work, and we specifically covered a buck regulator. We talked about layout issues and guidelines related to those layout issues. Today, in part 2, we're going to introduce some FCC requirements and explain some testing and explain the impact from your layout. And since we focused on buck converters last month, we're going to talk a little bit about boost converters. And then in general, we're going to talk about load regulation and efficiencies of the switchers themselves. And as always, if you're interested in learning any more about this presentation or any of the previous presentations, please feel free to reach out to us and we will help you find the appropriate information. So before we get started, we like to offer the first polling question, as always, try and get your feedback on why are you attending this webinar? Okay, so it looks like about 68% just want a better understanding in general. That's good. Okay, I appreciate that input. And I do have one more slide for you, if you don't mind. One more question for you. And this question that's coming up is more just about why are you wanting information on the FCC aspect? Okay. Great. Looks like most of you all are just wanting to improve your toolbox. Good. Well, thank you again for that input. Okay, so in order to understand today's lessons, we do have to do a little bit of a review just to make sure, because it's been a month since we did part 1. Try and go through this and hit the highlights. So in general, the concept of a regulator is to convert one power supply voltage to another. Like we did in last month, we talked about if you plug in your device in the USB port and your device runs on a 3.3 volt rail, then you can't run it off of 5 volts. You have to have something to convert that voltage from one to the other. And generally there's 2 types. We talked about one of the more common ones is called a linear. A linear is very simple, easy to implement. The only problem is it does waste energy, but it gives you low noise and low EMI issues because it's basically just a resistor. And so therefore, it'll typically waste energy. The switcher, on the other hand, is something that you'll use a lot because even though it's more difficult to implement, it's usually very highly efficient. So therefore, you're not wasting energy. The big problem is with a switcher, you could possibly have some EMI concerns. When we talk about switchers, there's generally 2 types. Last month, like I said, we talked about the buck, and the buck decreases the voltage. Today, we're going to talk in a little bit more in depth about the boost, meaning that it's going to boost the voltage or increase the voltage. Both of them have the same basic elements. The only thing different is how they're configured. And we use little yellow circles and rectangles to denote the 5 basic elements. So you have the capacitor on the input, you have a switching circuit, which here is referred to as a Q or a MOSFET, and it's receiving some type of clocking signal. This is not a system clock, it's a clock driven by the actual switcher control circuit. Then you have a rectifying diode, and then you have a inductor that is going to be used to source current, And then you have the output capacitor, which is used to not only filter, but also supply the constant voltage as much as possible to the load. So let's take a review of the buck regulator in operation. In phase one, we're showing on the right-hand side, the blue loop. Blue loop is showing the general current flow during this phase. And during this phase, we turn the transistor on. That allows the current to come from the input capacitor, which will have a good charge on it, through the transistor. And the purpose is to build up current flow through the inductor and therefore build up a magnetic field around the coil, and then charge the output capacitor to the desired voltage. This blue line that you see is what we refer to as a power switch loop, and that's going to be dominant during this phase of operation. The second phase, which you see in the orange loop on the right, that happens when the transistor turns off. When the transistor turns off, the coil is now going to act as a current source. It does so while it's discharging. And since it's discharging, then the current goes through the capacitor and then back up through the diode and into the inductor again. We've referred to this orange loop as the rectifier loop, and it dominates during this phase. The boost regulator, if you'll notice on the right-hand side, has almost exactly the same type of concept. In phase one, we're going to use the same blue line to show a charging phase. We're going to turn the transistor on, and we're going to allow the current to come through the inductor, build a magnetic field, storing the energy as a magnetic field while that transistor is on. That happens through the MOSFET. During this charging phase, again, the power switch loop dominates. But notice, now we're talking about the loop being at the beginning of the circuit. So it's going to be between the input capacitor, inductor, and then the switching IC itself. In phase two, again, we go back to an orange loop. And this time, your transistor is turned off. When your transistor is turned off, then the inductor is going to collapse its field again. But notice that when it discharges, now if you look over here on the right-hand side, that the polarity of the voltage coming off the inductor flips. And when it does, now you have basically two voltage sources that are in series with each other. One source is the voltage on the capacitor on the input, and then the inductor acts as another. So they are now in series. Because they're in series, we're providing a boosted voltage through the rectifier to charge the output capacitor. Again, we refer to this as a rectifier loop because it's going through a rectifier. Remember, in both the buck and the boost, it is the high DI/DT transitions that are going to be causing all your EMI issues. So in conclusion, both the buck and the boost have the same basic elements. Even though they are configured differently, both are going to have the same issues with loop area. If you remember from last month, we talked about the physical location of these basic elements have to be in a tight-knit location, minimizing the current path as far as how it goes through these different loops that we're talking about. Because when you shrink that path and minimize it, then you're minimizing the loop area, you're minimizing the amount of fields that can be coupled to other structures in the general area. So therefore, the same rules are going to apply. You want to maximize your trace width, therefore you're minimizing your inductance of the trace, and you want to minimize the trace length. That also minimizes the inductance and also reduces the resistance. Polling question number 3, okay. Yeah, so what is the greatest contribution to maximizing the trace width? Okay, looks like 37% of you all got the right answer, reducing the loop inductance. I noticed that quite a few of you all put E, that answer both A and C. So the trace width does not necessarily reduce the loop area. So that's why I put C as the correct answer. So very good. Okay, so the next section, we'll talk about converter efficiency. So efficiency of a switcher, as always, when we talk about efficiency, is the power delivered to the load based upon the amount of power delivered or coming in from a source. And you always want it to be 1, but that's an ideal situation. In our situation in the switchers, you'll typically see efficiencies in the 80 to 95%, depending upon configurations. But one of the biggest sources of loss is the rectifying diode. And that loss is going to be there because you have current going through the diode, and it's a function of that forward voltage. Reverse recovery for silicon diodes can also impact the loss. So one of the first solutions that you'll see in most of your data sheets for converters is to utilize a Schottky diode. Schottky diodes have a low forward voltage, and they are also very fast switching. So again, your typical efficiencies are still going to be in the 85 to 90% range of typically. Now, another approach having to deal with this loss in that Schottky diode is to use a MOSFET in place of the rectifier. What you see in the bottom of your screen now is what's known as a synchronous rectifier design. There's 2 phases. The first phase, we call it on phase. Again, this is a simplified version of a buck converter. So because the inductor's on the output. So during the on phase, just like before, your FET was turning on. That's this FET up here at the top. That FET turning on would then put current through the inductor, charging the output capacitor, building up the magnetic field that's in the inductor. And during the off phase, the upper transistor would then be turned off, and the lower transistor, where you would normally see the diode, the rectifier diode, that one's going to be turned on. The operation must be a break before make to prevent cross conduction. If you're not familiar with this, basically what we're trying to say is that if for some reason this device is very slow to turn off, and I turn this device on, the rectifier portion of the FET, then VN could possibly be shorted right to ground for a small amount of period. It's called shoot through. And so that's bad. So there's always going to be a little bit of time between this transition that we refer to as dead time. And during this dead time, you actually are using the diode portion of this bottom FET to allow current flow. But once the FET completely turns on, now the forward voltage of the FET is what ends up being your loss. And if you're familiar with FETs, that RDS could typically create only a few millivolts voltage across it instead of, let's say, 200 millivolts that you might see in a typical Schottky. So you can see that you got quite a bit of difference in loss has been reduced. Now, the problem with switching converters, a lot of times your load is not consistent. You may end up getting in a situation where you're in light load, you're not pulling enough current to keep it running in a normal continuous operation. So to understand the light load situations, let's talk about the 2 different modes of operation of your switchers. You have continuous and discontinuous mode. Now, all of our discussion so far has always referred to the left-hand chart or picture here of a continuous mode, where the FET that's charging your inductor is turned on, so you have current flowing through the inductor from your source, and then that charging FET turns off, and then all you have, your inductor is acting as the source, and the current's going through the rectifier diode. And then, so you have this building up the magnetic field, collapsing of the magnetic field. Oh, sorry, I clicked. So during on time, we're building up the magnetic field, and off time, we're letting the magnetic field create a current source in the inductor. And then the cycle just repeats. But if you don't have to have that much power coming out of your regulator, then you can end up going into what's called a discontinuous mode. In this situation, the FET turns on, builds up your current in your inductor, but it ends up being that the inductor completely discharges and it doesn't come back on for a while because your output voltage on your capacitor is staying high because its energy is not being drawn out of it from your load. So you have this little dead period here where your regulator is not providing any energy, just the output capacitor. But because most of your circuits will always be working in a continuous, that's the more common thought pattern of how they work. The problem is when you get in low draw situation that you're going to transition from that continuous to a discontinuous mode. Now, the interesting thing about it is when you go into the discontinuous mode, your efficiency is going to increase. But why? Well, if you think about it, if there's no current coming out of the inductor, then there's no losses in the inductor. There's no current flowing through the rectifier diode, so there's no loss through that diode. And there can even be less loss in the switching transistor itself because it's not having to come on as often. So what I've put up here on the right-hand side is a little chart that kind of summarizes the continuous mode on the right versus the discontinuous mode on the left. And a couple little areas here to help you understand. But the thing I want you to understand at this point is that when you're in continuous mode, the efficiency is less, but when you go to discontinuous mode, your efficiency increases. Now, when we get into discontinuous conversations, you need to understand that there are two different modes of operation. You have a forced pulse width modulation. That is, it's a fixed frequency. The only thing that changes is the ratio of on time and off time. Another type is called skipping. That is where the frequency of the pulse changes. In your forced PWM mode, the nice thing about it is your noise spectrum is constant. It is therefore easier to filter. It's also easier to find a source of your signal. So if for some reason you have a situation where you're failing your FCC or you're prepping to go to your FCC testing and you see noise, because it's constantly there, then it's easier to trace down. You can also target your frequencies. So say you have a product that you know is going to operate in a certain band, and now you have to put a switcher in there. Well, you can find a switcher that hopefully will operate in a frequency band other than what your main product is supposed to be working in. If you go to a skip, you do this because you're trying to increase efficiency. If you have a product usage case where, let's say it's a satellite and power supply, and you need to make sure that it doesn't waste any energy whatsoever in a very light load situation, well, then you may go to a skip type of discontinuous mode. Yes, you increase efficiency, but it makes it harder when you're doing the design if you have any problems with noise. And the reason being is that it's not in a fixed band. It's also more difficult to filter. But because the frequency is changing as the load changes, then the noise may only appear under a certain load condition. So therefore, when you're testing your product and you implement a skip type mode to increase your efficiency, you need to make sure that you change your load accordingly from the minimum to the maximum and look for any noise spikes that occur as you're changing the load. Now, this comes from a Maxim chip where they give you the option of going from a forced to a skip. If you notice in a forced on the right-hand side with a little diamond shape, when you're down here at, let's say, 10 milliamps, the efficiency is really bad. At 100 milliamps, it starts to go quite high. When you get to 1 amp, now we're getting up that 90% efficiency. But if you go to a skip function, notice that it goes up quite quickly, up to 80%, even at light loads. And then they're about the same once you get past 1 amp. Okay, the next thing we're going to talk about is load regulation. So every switcher that you put together is going to have a feedback loop. You're probably familiar with the 2 resistors. You have a feedback resistor, and then you have the ground resistor. And that creates a voltage divider. And that voltage divider provides a voltage that is compared to a reference voltage internal to the chip. And then as that voltage changes, that's how the switcher knows what the duty cycle needs to be on your continuous mode of operation. The question comes down to is, where do you physically put this feedback network? So there's typically 2 locations. You're either going to put it right next to the switcher, or you're going to remote it with the load. If you decide to put it at the switcher output, you're going to do so when the load is either not very far away from the switcher, or you have a very low impedance path to the load. But if that's not the case and you want to remote it with the load, you'll do that in order to make sure that the switcher can monitor the voltage at the load that is trying to maintain. And you do that because you want to compensate for your path loss. That is your voltage drop. So if you're generating, you're set up with your voltage divider to generate 3.3 volt, but let's say you don't have a very low impedance path and you're pulling 10 amps out of a switcher, you could easily drop 100 millivolts over that path. So if it's important to have the exact voltage on your load, then you're going to remote this feedback network. The nice thing about remoting it is it gives you a faster response to your load changes. Of course, you may be asking yourself, why is that the case? Well, if you think about it, you have inductance along your path for that feedback, but the inductance affects the ability of the circuit to change potentials. But if it's on a low current path, then that impedance is not as much of a problem. So now the feedback network can actually feed that signal back faster than it would be trying to deal with the voltage drop across the actual source path. Okay, so the next section we want to talk about is the FCC. If you're not familiar with the FCC, it stands for Federal Regulation Commission, and there's a website, and we're going to specifically talk about Part 15. There's a nice little link here. If you ever want to look up an an FCC ID number, and you can get test reports and to give it examples of what a test report's going to look like. So the next thing is we want to talk about the regulations for computers and other digital devices, because that's primarily what we're dealing with in this audience. So the FCC is going to establish limits on what frequencies and the power that can be allowed to radiate from your product. Now, when I say radiate, I don't necessarily mean like from an antenna. It could also be conducted, and we'll talk about that more in a minute. But one of the main concerns of your design is how the frequency content will be tested in order to stay within these limits that the FCC has set up. Now, the FCC is going to define a digital device as any device or system that generates or uses digital timing signals greater than 9 kilohertz, which I think for probably 99.999% of all this audience, you would fall into that category. Now, in order to prevent the radio noise generated by a digital device from interfering with radio communications, that's really what this all started with, is making sure that you didn't interfere with people's TVs and radios. The digital devices must be designed to contain the noise, that is, any high frequency content. And you're going to limit radiated emissions. You're going to do so by designing a digital circuitry in a manner that minimizes your radio noise emission. You will also try to enclose the circuitry in a manner that's going to prevent any of your radio noise from escaping. Now, the other type of emission is called conductive emissions. If you have a product that ends up plugging into the wall to get power, then this is going to be germane to your type of design. It's going to include a well-filtered power supply that keeps the radio noise from leaking into the electrical power lines. The FCC does not want your product putting a bunch of noise back into the system, the power system. So they have tests set up to make sure that your product is limited at how much it puts back on the power system. So let's talk about the FCC certifications themselves. The FCC is going to require that tests be performed on your device that's going to be authorized. These tests or verifications are going to measure, quantify the levels of RF energy that are going to be radiated by the device into open air or conducted by the device onto the power lines. After these tests are performed, you're going to have a report, and that report must be produced showing the test procedure. You're going to get your test done at what's called a certifying lab. These are labs that basically have been certified to meet these guidelines, because ultimately the FCC wants to know that every lab that performs a test would be generating the same type of test report if they were to take a given product and take it to every lab. They want to make sure that all the labs are creating the same type of report. You're also going to have other additional information about the device, including design drawings. Now, there is specific information that must be included in this certification report, and all that is detailed in Part 2 of the FCC rules. Once the report is completed, the manufacturer, or if you're importing a device, you'll need to do the same. You'll have to keep a copy of it on file as evidence that the device meets the technical standards in Part 15. Now, for the fun stuff, Part 15. Part 15 has 8 subparts, A through H. Subpart A is just some general information. Subpart B is for unintentional radiators. That's basically exactly what it says. It's for something that when you design this product, you're not expecting it to radiate any signal whatsoever. Like if you put together a clock radio and no Bluetooth, nothing like that to communicate outside of it. It just gives you an alarm clock. That's not supposed to radiate anything. Subpart C is for intentional radiators, let's say like a remote or a phone. Subparts D and H, they don't really apply to our discussion today, so we're not going to get into them. Subpart C is actually quite detailed, and we're not going to get really deep into intentional radiators today, because ultimately we're talking about DC to DC switchers or power supplies. None of those are designed to be intentional radiators. So let's talk about unintentional radiators and expand upon that in subpart B. Here you have a picture of just a Cisco network switch. The category of unintentional radiators are going to include a wide variety of devices that contain clock or oscillators and logic circuitry, but that do not deliberately generate radio frequency emissions. Okay, so there are going to be 2 levels of radiation and conducted emission limits for unintentional radiators. and that's also specified in subpart B. It's kind of important to understand that not only are you looking for radiation and conducted, but within subpart B, it depends on the type of product as to what those limits are. Your product is going to fall into one of two categories. Class B are those devices that you might be designing that are marketed for use in anywhere, including residential environments and by anyone in the general public. I got a picture here of a computer monitor, and again, the little alarm clock. Class A, these are devices marketed for use in an industrial, commercial, business application, and is not intended for use in the home by the general public or in any residential area. And the reason being, again, we have two different sets of limits for the type of product that you're going to be creating, because the Class B devices pretty much can go anywhere. They're ultimately going to be more stringent because they need to be able to be compatible with everybody else's product. Intentional radiators, subpart C. Intentional radiators must either have a permanently attached antenna or provide a unique coupler to prevent the use of an unauthorized antenna, such as your cell phone. Your cell phone has all kinds of different communication needs in it. It has a Bluetooth, has Wi-Fi, and it has a cellular communication. So there's three different types of intentional radiators on a cell phone. Each one of them is going to have its own unique antenna or method to get the signal out, but in a very controlled method. And each one of those is going to have to be tested. Subpart C has rules for operation of these transmitters. They're very detailed regarding the fundamental field strength, the power density, the frequency accuracy, and the permitted harmonic and spurious emissions. Like I said earlier, there's a lot that goes into this test, and that's not the focus of today's webinar. Again, DC to DC converters do not fit in this category. So you may have heard a term called CISPR. People seem to throw that around quite a bit too. And in our situation, when we talk about information and technology equipment, you'll hear CISPR 22 used. But that is a standard for EMC within Europe. There's also another related standard called EN 55022. It is a modified derivative of CISPR 22. And as a result, both standards are used widely within the industry. But it's important for you to notice that Part 15 and CISPR 22, even though they've been made relatively harmonious, there are differences. So you need to be aware of those things. If you are going to have a product that's only going to be in the United States, then you only have to worry about Part 15. If it's going to go to Europe, then obviously you have to be worried about CISPR 22. You need to make sure that you investigate carefully the differences between the two. CISPR has a similar EMC standard for other types of equipment. There's CISPR 25 for like automobile and boating equipment. And you can spend quite a bit of time just seeing what the different CISPR standards are. Okay, now let's get back into the subpart B. And we're talking about unintentional radiators, like you see in this chart up here, unintentional radiators. Remember, we have two different types of limits. We have conducted limits and we have radiated limits. And we have conducted limits for Class B and Class A, depending upon where the product's going to be used, and the same thing for radiated, Class A and Class B. You may notice in here they talk about quasi-peak and average. That's just the different type of sampling that the test equipment can use. In today's discussion, we'll be talking about using average. So the first part is the conducted emissions that we're going to talk about. So you can see on the left-hand side a graph showing the Class A and a graph showing the Class B on the right-hand side. DC switchers can cause failure of both conducted and unintentional emission test. So for now, we're going to talk about the conducted failure portion. The conducted emission test in the United States covers 150 kilohertz to 30 megahertz. There is a really nice video explaining the concept of the testing in detail, and so I put this in here. It's very informative. Just take a look at it whenever you get a chance if you want more information. So in the conducted emission test itself, you'll see in this screenshot a typical setup of your device under test. And it also shows all the spacing requirements. These spacing requirements are more for the radiated portion and not the conducted, because remember, the conducted emission is seeing how much noise is getting out on the power line. So it actually stays in the wire. If you're wanting to see how much the product is radiating, then you need to basically treat the radiator as an antenna. So your antenna has to have a ground plane. And so they have very specified distances of the table height, how much ground plane there has to be, so that it is compared equally no matter what the product is. Now, to do the conducted, you have to have what's called a listen. Here's a picture of any generic listen. You can buy them. It's nothing special about them per se that you have to have a certain license to get them, but every test lab is going to have one of these. Your listen is called a line impedance stabilization network. Again, we're going to be working on making sure the noise doesn't leave your product and get on the power system. So that's what this is stabilizing. So we want to provide a well-defined RF impedance to your product that's being tested. It also wants to provide a low impedance path for the noise to be measured at the output port of the listen coupling, the interference voltage generated by your device through a 0.1 microfarad decoupling cap to the analyzer or receiver. And the role of this product is to isolate your differential mode currents and common mode currents from the power supply itself, meaning the wall outlet, and to minimize the impact of your common mode current by returning it back to the source. So there are several types of listens, but here's just a single port schematic. The first one is the one that you're going to be becoming more familiar with in this particular type of test, is the V-listen. Basically, it's a line to ground. So if you're familiar with when you plug in a cord, you typically have a white, black, and green wire. So this would be for the black wire or for the white wire. You also have a delta listen, which we're not going to get in today, and a T-listen. Within the V-listen, you need to be aware that if you start doing a little searching on the internet, you'll find out that there's actually two different types of V-listens, and it's based upon whether or not, or the size of the inductor. If you're going to be working with CISPR 22, which is probably what most of you all will be doing, you'll want to have a listen that is set up with a 50 microhenry inductance, basically because you're going to be operating on mains of 50 and 60 hertz. But if, let's say, you're going to be working on vehicles and boats and aircraft that may be using anything from DC to 400 hertz, then you'll have a listen that's set up with 5 microhenry inductances. Now, what you see here is a diagram. On the right-hand side, you have your power cord, and then on the left-hand side is your product that would be getting tested. So you would have your hot and your neutral and your green or ground wire. So again, the purpose of this was to allow for each line. If you'll notice, here's your hot comes in here. You have a DC blocking cap. The DC blocking cap prevents any DC from your product going across this 50 ohm impedance of your receiver or your spectrum analyzer. You'll notice you also have two 50 ohm resistors shown here. you want to make sure that you have in your listen this dummy load so that your system is balanced during the test. Let's see, next, here's your 50 ohm inductor. Of course, this does two things. This makes sure that your noise, whatever you're generating, does not go out to the power supply itself, to the wall. Any noise that is out here in the power system that might come in, that's also shunted through the 1 microfarad cap. And the 50 microhenries is used to make sure that you don't get any noise into your test from the external power system. So the noise that your system is generating comes through the blocking cap, comes out and goes to the spectrum analyzer. That's how it determines how much noise there is going to be measured. Okay, so let's just take an example. So we're going to have a Class B product, which is probably a lot of what you all are going to be designing. And let's say we want to look at an average limit. That average limit, if you'll notice on the right-hand side, I've got it set up to about 45 dB microvolts. Now, since the limit is in dB microvolts, you may or may not be familiar with how that relates to the real world. And what I mean by real world is everyday working environment, people don't use dB microvolts typically. So they do look at voltage on, let's say, an oscope. So a dB microvolt, the equation for it is 20 log base 10 of the noise voltage itself in microvolts as it relates to 1 microvolt. Kind of like power is in the RF world. You have dBm versus dB. It's all related to 1 milliwatt is 0 dB. I'm sorry, it's dBm. So if we rearrange the equation and we're going to look for how much noise does that really mean that I can have on my output, you just take 10, raise it to the standard, which is 45, divide it by 20. And when you do that, you come out to a noise level of about 178 microvolts. Now, you think, wow, that's not very much. No, it's not. But also remember, and this is important, that is the voltage measured across 50 ohms. So you can't just put your oscope on there with a 1 meg ohm input impedance and measure it and say, oh man, I've got 200 millivolts. That's too much noise. Well, you got to make sure you shunt it with a 50 ohm, and that'll change what your voltage is. Okay, so now we finished the conducted emissions. Now we want to go into the radiated emissions. What you have on the right-hand side is a chart that shows a test that's going to be based on two different things. It's going to be based on the class of product and the distance. If you notice in the chart in the bottom, you'll see Class A 10 meters, Class B at 3 meters, and then the actual numbers. And then here's a graph to kind of show them in perspective. Class A is in the red, Class B is in the black line. And then note the frequencies in which the standard is the same. In this case, 88 megahertz to 216 megahertz, the standard is the same voltage. So when you look at this graph, you might have the initial thought, say, well, wait a minute. A, which is in red, that's a lower number, especially down there in the lower frequency range. That must be a tougher standard to have to deal with. But the problem is, if you noticed in that previous chart, though, the distance in which you measured it was different. You had 3 meters and 10 meters. So if you take the 10 meter and you deal with the fact that you now have a signal loss from that extra 7 meters of distance, and you create a graph that actually shows the same relative scale for 3 meters, you can now see that actually Class A is much less stringent. This is Class A up here. And why is Class A less stringent? It's because it's typically those are the products that are going to be in an industrial situation. The FCC knows that those devices are going to be noisy, and they're not as worried about them playing well together. They're also not worried about people not being able to listen to their music on their portable radio or watching TV. You remember FCC got its start a long time ago when people were worried about getting interference with their radios, specifically any of the radios used in the military. So if you have a product, you want to be very cognizant of the penalties that FCC can put on you if you decide to sell a non-compliant digital device. You could be subject to quite a bit of enforcement action by the Commission's Field Operations Bureau, and it could result in one or more of the following: forfeiture of all non-compliant equipment, $100,000 to $200,000 criminal penalty for an individual organization, a criminal fine totaling twice the gross gain obtained from sales of the non-compliant equipment. That could be quite substantial. And an administrative fine totaling $10,000 a day per violation. Again, that could be a lot of money. Section 15.103 is going to details digital devices that are exempt from these technical standards in Part 15. So if you are creating a new product, you might want to go in here and see, oh, well, we don't even have to be worried about complying. It doesn't mean that automatically you don't have to be concerned about radiating signals. It's still a good idea to just double check. But if your digital device is used exclusively in appliances that are designed to heat, cool, or move something by converting electrical energy into heat or motion, let's say like a vacuum or a blender or your central heat and air, those devices don't have to meet Part 15. If your digital device is used exclusively on any transportation vehicle, it doesn't have to be subject to Part 15. Specialized medical digital devices, if they are used exclusively as industrial, commercial, or medical test equipment, again, make sure that you understand when it says exclusively, as with any government agency, you have the burden of proof to show that it's used exclusively. And then, of course, any digital device that has a power consumption of 6 nanowatts or less, such as digital watches and solar calculators. Pay attention to that term exclusively. Okay, we have another polling question for you, if you don't mind helping us to get a little bit better understanding. We just want to know, how do you plan on getting your product certified? Okay, so it looks like quite a few all are planning on using a certified test lab, 83% of you. Okay, so I've been through this process several times, and just a word to the wise, if you've never gone through the process before, the lab technicians are very helpful, but they are not there to help you figure out why your product is failing. They're very good at helping you to see that it's failing, but don't expect them when you're there to offer any critiques or make any suggestions, anything like that. That is totally up to you and your design. So just a word to the wise. Okay, polling question number 5. Just a general question. Why could a switcher in skip mode be a potential EMI problem? Okay, good. 36 of you all got the right answer, B. The thing you have to understand is, if you remember from the last part 1, we talked about structures acting as antennas. Well, structures act as antennas when those structures are at specific wavelength multiples of the signal that's oscillating on that structure. So a trace that may just be open is not going to act at an antenna at every frequency. So as your load changes and that frequency of operation changes, then there's only going to be certain loads that'll cause certain frequencies that'll couple to this one particular structure that may have a tendency to resonate at that one frequency. So being in a skip mode means that you could more likely be an EMI problem creator, because you might have some resonant circuit in there that's going to be treating it, that signal, as a stimulus, and so it's going to acting as an antenna. So that's why it could very easily be an EMI problem. Great. Okay, in summation, there are two loops that are the most concerned. Both of them are the same as far as their terminology, the power switching and the rectifying. And they exist in both topologies. That both converters have similar EMI issues because they both are dependent upon the loop area. Minimizing that loop area is going to minimize your chance that it's going to radiate any signal. And DC switchers can be a source of failure of EMC compliance due to switching noise, whether it be radiated or coupled through the power supply. Coupling through the power supply is referred to as the conducted emission. And then the radiated is when structures act like antennas. Well, if you don't mind, I would like to see one last question. As always, I'm interested to find out how you all feel about today's material. Well, that's great. I'm so glad to see that 94% of you all felt that this was relevant for what you needed. Okay, well, with that, I will go ahead and turn this back over to Paul so he can talk to you. And I know we started late, so I'll look for some questions. And if you all want to stay for the question and answer period, I'm more than willing to stay on the line, and we can address some of those for just a few minutes.
Thank you very much for joining us here today, and we will see you at our next webinar that should be slated for the 27th of